Okay, so we're taking a look at section 3.2 today. Section 3.2. We can kind of think of section 3.2 as theoretical considerations. So some of the stuff that we've already done. Oh, my chair's getting squeaky. Let's see if I can move it over. Some of the things we've already looked at is one. Jeez, I need a new chair. The existence and uniqueness theorem, right, for our second-order differential equations, second-order linear homogeneous differential equations. Right, with our initial condition, so y of t0 equals y0. This is our initial velocity. Right, and what we said was that we need an interval on which p, q, and f are all continuous on an interval containing, open interval containing the point t0. So let p, q, and f be continuous on open interval I containing t0, and we want to take I to be the biggest such interval, right? Then there exists a unique solution. Remember our notation? There exists a unique solution to the IVP. And it persists, I guess you could say, on the entire interval I, valid on I. So we're able to predict, just like we did in the first order, what interval our solution exists on, right? Without actually solving the differential equation. Good. What was some other theory that we looked at last time? We looked at linear operators. And just as a reminder, the word linear here, right? So L is a linear operator. L is a linear operator if for every scalar A and B, or maybe I think I was using C and D, and functions f and g, the following is true. L of f plus g is equal to L of f plus L of g, and L of c times f is c times L of f. Okay. Now, some people will combine those two things into one, and that is fine if you want to do it. So, alternative way of saying it is that L of CF plus dg is equal to C times L of F plus D times L of G. Okay, so either way you want to say it, I think the physicists like this one better because this actually represents a certain principle that we talked about last time. Do you remember what it was? Superposition principle. Yes, we'll talk about that in just a second. All right. So what we showed also was that a differential equation is linear if its operator is linear. Okay. And so in particular, right, the second order linear differential equation can be expressed as L of y equals y double prime plus p of t times y prime plus q of t times y. Notice I'm not saying equals anything, right, because this is just the operator acting on y. Good. All right. Now what? So now the question was, we said that, let's go ahead and write down the superposition principle. So if y1 up to yn, I keep getting crooked, I hope you don't mind that, are solutions to the homogeneous DE. Let's go ahead and write it in shorthand notation as L of y equals 0, where this is my L, right? Then, so is any linear combination. That is C1y1 plus C2y2 plus Cn times yn. So this function also solves the linear first order or linear differential equation equal to 0. Okay, actually it doesn't matter what the order is as long as it's linear. Good. So now I'm going to rephrase this all in terms of the second order differential equation. All right, so let's get back to the second order differential equation. Suppose y1 and y2 each solves the second order differential equation. Let's go ahead and be specific here. So this is the specific first order linear differential, I keep saying first order, second order linear differential equation. But notice that we can be more general than constant coefficients, right? These are functions of t. What's important here is this is linear and this is homogeneous. Okay. Then the question is, suppose I now have, let's say that we have arbitrary initial conditions. Y of t0 equals y0 and y prime of t0 equals v0. Now the question is it always possible to find constant C1 and C2 so that C1y1 plus C2y2 solves the IVP. So what are we saying here? So what we're saying here is that I have two solutions to this differential equation, and I know that in general C1y1 plus C2y2 is another solution. The question we're asking here is, can all solutions to the arbitrary IVP, can all solutions with an arbitrary IVP be written in this form? Does everybody see the difference? So on the one hand, we're saying, well, if you do have two solutions to this, then this is also a solution. On the other hand, what we're saying now is, suppose I've got arbitrary initial conditions for my differential equation. Am I always going to be able to write the solution in this form? So somehow, I think there's got to be some kind of restriction on y1 and y2, right? Wouldn't that make sense? You couldn't just take two arbitrary solutions to this differential equation and then be able to write all your solutions in terms of those. There must be some restriction on y1 and y2. And we're going to see what that is now. All right, so let's go ahead and see what kinds of restrictions we're going to have. So I'm going to try to solve for C1 and C2 using these two initial conditions. So with the first initial condition, I've got y0 equals C1 y1 0 plus C2, t0, sorry, y2 t0. And then the second initial condition, I'll have v0 equals c1 y1 prime at t0 plus c2 y2 prime of t0. Okay. Now, in solving this, remember that c1 and c2 I can solve for by using Cramer's rule. And Cramer's rule gives me a solution guaranteed as long as what happens in the denominator? The denominator cannot be 0, right? If the denominator is 0, that means that Cramer's rule cannot be applied, and that means we have trouble with our y1 and y2. So on the flip side of that, if the denominator of Cramer's rule is not 0, That automatically guarantees that I can find C1 and C2. So what is the denominator? y1 of t0, y1 prime of t0, y2 of t0. It's the determinant of this, right? y2 prime of t0. So this is the determinant of y1 and y2 with y1 and y1 prime and y2 prime, right? So what we're saying then is that the answer to this, is it always possible to find C1 and C2? So this solves the IVP. The answer to this question is yes, if this determinant, let me write it big now, because this is our main result so far, is not 0, right? This is such an important computation that we actually have a name for this computation on the left. Definition, the Wronskian of y1 and y2. Or in fact, the Wronskian is defined just for two general functions. So the Wronskian of two functions f and g is defined to be Wronskian f of t, g of t, f prime of t, g prime of t. Now remember, this is a determinant, so I could go ahead and compute that. That's f of t times g prime of t minus f prime of t, g of t. Good. All right. I'm running a little late on this, so I'm going to pause this here, and then we'll start a new video, and we'll start right here at the Wronskian. Okay, be right back.